Hello everyone, Dhruv here from Comet, and today I am very excited to be demoing Kangas, a new open source data exploration and analysis library. So for those of you that don't know, Kangas is sort of like behaves sort of like a data frame, only it supports multimedia data and can scale up to millions of examples. So when debugging deep learning models, oftentimes you will be dealing with very large data sets. So Kangas is a way to analyze these data sets and sort of come up with insights around individual examples of the data. You can also use it to debug model predictions, which is what we're going to be doing today. So today we will be focusing on using Kangas for object detection. So I mentioned that Kangas is a multimedia data frame or behaves like a multimedia data frame. And right out of the box, as of this moment, natively supports object detection use cases, image segmentation use cases, and image classification use cases. With more use cases to follow, look out for audio and text coming sometime soon. To sort of demo these use cases, what we're going to be doing today is walking through an object detection problem. So I'm going to be using the OWL VID object detection model, which is a open vocabulary object detection model. So what this means is this model wasn't trained on this data set or on these labels whatsoever. It uses CLIP as a backbone under the hood. And so you supply the labels at inference time. And then the model makes a guess as to which label fits which bounding box. So we're going to be using the Fashionpedia 4 categories dataset for this problem. And there are, these are the 4 categories. It's accessories, clothing, bags, and shoes. So at inference time, we will supply this list to our model, and it will output a prediction of a set of bounding boxes and will assign a label to each of these bounding boxes. So once we have our predictions, what we're going to do is we're going to annotate an image with these predictions. We're also going to annotate the image with our ground truth labels and save all of these to a data grid. And then we're going to fire up a Kangas server and explore our data grid. And we'll walk through what you can do with the Kangas UI and how you can use it to sort of debug your model predictions. So this tutorial consists of 3 parts. Really, the first part is just installing the dependencies. So we'll be using Hugging Face transformers, Hugging Face's datasets library, Kangas, obviously, and I think Cornea to compute a mean average precision score for our object detection model. Then we will run a detection script. The detection script is basically responsible for downloading our dataset, sampling a few examples from the dataset. We will only be using 500 examples for this demo. And constructing the data grid. So it will take the model predictions, annotate the images, add some other useful metadata, and save it to the Kangas data grid. And finally, once we have our data grid, we're going to fire up our Kangas server. So you do that by running Kangas server. And that will bring up the Kangas UI, and you can use that to explore your model predictions. So now we're going to hop over to our detect.py script, and let's just take a look at what's going on here. So the first few lines are just setting up parameters for the script. So we're importing our libraries. So we're going to be using the Hugging Face datasets library, which will load in our dataset, and we'll also use the library to sample a few examples from our dataset. We're using Cornea to compute a mean average precision score for each of our model predictions for an image. We're going to be using torch vision to apply non-max suppression on our object detection predictions. So non-max suppression is a way to basically consolidate overlapping bounding boxes if those bounding boxes belong to the same prediction. So if you have, if your model has predicted 20 bounding boxes, all belonging to a particular class, what non-max suppression will do is it will consolidate all those 20 boxes into a single box based on the confidence score for the class in each of those boxes and the overlapping area between the boxes. We're also using transformers. This is where we are fetching our model. So we're going to be fetching the model from the Hugging Face hub. The model is from Google, so it's the OWL VIT model. You can find it at this path on the Hugging Face hub. Similarly, the path for the dataset is under the detection datasets repository, and it's called Fashionpedia for categories. We'll be using the validation split of the dataset, and we're going to be using 500 examples from the validation split. We have over here just some thresholding values for our predictions. So this is what is going to be used as inputs to our non-max suppression algorithm. So the IOU threshold will tell us whether to count an overlapping box as the same box. So if two boxes overlap by 50%, non-max suppression will consider that to be the same box. So that's this is a hyperparameter that you can tune, but I think most libraries default to using an IOU threshold of 0.5. So we're also going to be using an IOU threshold of 0.5. The score threshold, this is just an additional threshold I introduced here. This is a confidence score threshold. So with object detection models, you tend to have many predictions that for bounding boxes with low confidence. This tends to basically produce a lot of noise in your predictions. So to sort of get rid of those low confidence predictions, I'm just setting a sort of floor for the confidence value that we would consider. So that floor is sort of 0.2. This is also a hyperparameter. You can obviously tune this. This is just a good value to start. The next section I want to highlight in the script is the actual construction of the data grid. So first, what we do is we extract the class names from our dataset object. So we load in our dataset using Hugging Face, and then from this dataset object, we can access the class labels that are present in the dataset. So that's this line here. And this varies from dataset to dataset, but for this dataset, this is how you grab the class labels or the class names. And once I have the class names, I'm going to go ahead and define the columns for my data grid. So the three columns that I know I want in my grid are the ID. This is just an image ID, so I know what image I'm making a prediction on. So it's just an ID that's already present in the dataset. The image column is the column that will contain the image itself. And an MAP column, that's the mean average precision score that the model predictions for that image received. Additionally, I'm going to add some columns. So I'm going to add a column for each class that's present in the dataset. So the reason I'm going to do this is so that I can do some groupings for later on. So for each class that is present in my dataset, I define this column. And then when I have a prediction for an image, that will be a row in the dataset. And so if an object of this class is present in that image, I'm going to update the column value in that row to be a 1. And if it's not present, I'm just going to let the column value be 0. So it's just a way to indicate, easily see whether or not an object is present in an image or not. And then sort of to follow up on that, using the model predictions, I'm going to define another set of columns, which is called score underscore class name. So I'm going to use the model predictions, the model confidence scores for an image to define these column values for a particular row. So the confidence score for each of the object classes will be added to these columns. So what I'm expecting to see is if a object is not present in an image, this score should be 0. So that the model should basically output a 0 confidence score for the class being present. And if it's outputting a high confidence score bounding box when an object is not present, so that's that basically becomes a way for me to tell the model is making a lot of false positives. So that's why I'm adding this column for the score. And then I define my data grid. So this is the data grid object. I just give it a name, and I then pass in all the columns I just defined. The next section is just a bunch of helper functions. So these functions will help me do things like fetch the predicted score for a class label, apply non-max suppression onto some predictions, apply my score filtering threshold, and then another one for annotating the data grid image. So why do I have this function to annotate a data grid image? So the data grid image, we've sort of imported it up here. This image object will basically take in the PIL image that we get from our data set as an input, and it contains a number of useful methods that we can use to annotate our image. So I mentioned before that DataGrid comes with out-of-the-box support for object detection and image segmentation. So we will pass our PIL image to this DataGrid image object, and then we can use those methods to automatically annotate the image, and that will show up in the UI when we open up our Kangas server for analysis. So you can see here, we have a DataGrid image, and then we have the option of adding bounding boxes. So I'm adding the bounding boxes for, in this case, it's for a label. And I'm also adding the actual like text label to this bounding box. So if it's a ground truth label, I just add a prefix. So I add this GT prefix so that I know later when I'm looking through the UI, this bounding box corresponds to a ground truth label and not a prediction label. And then the next half, this whole loop right here, is just going through the individual examples in the data set. We are extracting the image ID, the actual image itself, creating a data grid image from that PIL image, annotating our data grid image, processing our inputs. So here I mentioned that OWL VIT is an open vocabulary object detection model. So it's at this point that we supply our class names as our like target labels, or the text that we want the model to detect within the image. And based on this list of text input, the model will come up with some outputs with bounding boxes for these text labels. And once we have our predictions, we apply our post-processing, which will basically scale the bounding boxes to the appropriate size for the image. I apply the score thresholding to remove all bounding box predictions that are less than, that have a confidence score of less than 0.2. And then I apply the non-max suppression on the remaining bounding boxes so that overlapping bounding boxes corresponding to the same class sort of collapse into a single bounding box. I then compute the mean average precision. So this is the average precision for all the detected bounding boxes for an image, and save that score as a row in my data grid. So after I've extracted all my predictions and annotated my data grid image with the label, the ground truth labels, and the predicted labels, predicted bounding boxes, I'm sorry, I construct a row in the data grid. And so the row would have the ID, the image itself, the mean average precision score for the image. And here is where I'm adding the presence of an object, the columns that indicate whether or not an object was present in the image. And here I'm adding the scores for the predictions for that particular object class in that image. And once I've done all of that, I've basically defined my row. I add my row to my data grid using dg.append. And then finally, we will save our data grid. And then you'll see in your folder this fashionpedia.datagrid file. So let's take a look at what this DataGrid file looks like in the UI. Okay, so now let's take a look at our DataGrid UI. So we're going to start our DataGrid UI by just running this command, just Kangas server. And that will start the backend server, start the front end, and just open up the DataGrid UI in our browser. Okay, so here we have the DataGrid UI. It looks a little bit like a spreadsheet, but that's sort of, we have rows and columns, but that's sort of where the similarities kind of end. There is this drop-down selector. So any .datagrid files that are present in your current working directory will show up in this selector. So let's select the fashionpedia datagrid file. That should load that in. And you can see we have all the columns that we defined before. So we have our image ID, we have our actual images, the map score, the columns for the class names that denote whether or not an object was present in the image. So in this particular image, we have accessories present, clothing present, shoes present, but no bags. And then on this side, we have the score for each of these predictions. So in this case, it looks like our model was not able to detect accessories, it was not able to detect clothing, but it was able to detect shoes. So we got a confidence score for shoes, but we did not get a confidence score for any of these other categories. So there are some false negatives that might be present in our model predictions. So that's sort of some of the insights that you can gather. We'll start exploring this data set in a little more detail. I just want to talk about the UI a little more. You can basically scroll through pages of these images down here. You can see that we have 500 examples logged, and that corresponds to the number of examples we sampled from our data set. If I wanted to flip through the pages, I can just go click on these arrow buttons. That will bring me, will basically scroll through all our image data. And if I wanted to go all the way to the end, I can click this double arrow button, which will take us back to the page, will take us to page 50, or I can go all the way back to the first page. So other things that you can do, there is a sorting option. So we can sort our data grid based on any column. So I could sort by the MAP score, and I could sort by descending or ascending order. So we can sort by the ones that have the highest MAP score, or we can sort by the columns that have the lowest MAP score. So this allows us to get an idea of the best and worst predictions. So predictions that we've done really well on, as well as predictions we're doing really badly on. We can also do a group by. So let's say I want to group by a certain object. So let's say I want to group by whether or not shoes were present in an image, and I want to see that does the presence of shoes in an image affect the overall MAP score. So that will sort of help me understand that all my high scoring images, maybe they have shoes in them, and all my low scoring images have no shoes in them. So I need to figure out. So my model is very good at detecting shoes, but not very good at detecting other things. So that's something I have to fix. So in order to figure that out, what we would do is we would select a column to group by. So we group by shoes. Okay. And we can see we have two groups. So we have a group with no shoes, and then we have a group with shoes, right? So that's, and then all the columns in the grid will update into these like nice bar charts to show the distribution of the other elements. And what we can see is the MAP score for images with shoes present is actually a lot higher. The distribution is further to the right than images without shoes. So that means that if we have shoes in the image, it's pushing the average MAP score up. And so this is something we want to address, because that means our model is not so great at detecting other categories. If we want to take a look at, so we could, if we were to group by another category or another class name, we could actually be reasonably sure that the difference in scores between the two images is probably due to the presence of shoes. And you can also see the distribution of other categories. So we can also look at, so we've grouped by shoes, but we can also look at the distribution of the other classes within those groups. So we can see that there's a greater distribution. So when there are no shoes present in an image, so this is shoes 0 in this group. When there are no shoes present in this image, there are also less of a chance of bags and accessories being present. But clothing is present for all images that do not have, the clothing class, is present for all images that don't have shoes, and the clothing class is present for all images that do have shoes. In the case of like accessories and bags, for images that don't have shoes, accessories and bags also tend to be missing. But this is also the case across the board. So what this is telling me is that regardless of the group, accessories and bags tend to be missing across images. Or rather, the distribution of accessories and bags is imbalanced across images. And that's just some of the things you can do with just the tools in the UI. And we haven't even gotten into using querying to filter your images. So in this basically filtering expression box that we have on the side of the UI, you can input queries, basically, that will let you filter your images based on code. So I could say select column name score shoes greater than 0.5. And this will give me all the predictions for images with shoes that have a confidence score greater than 0.5. So all of these images have a confidence score with shoes that are higher than 0.5. And then I can do a group by on whether or not shoes are present here to get an idea of, well, obviously shoes are present here because we've filtered for all images where the model gave a score for a shoe. So that this makes sense. But we can look at the distribution of the scores. We can even expand this plot in the UI, take a closer look at the numbers of the distribution of the MAP score. And we can open up our remaining images in this category to see what these images look like. And we can also, since we're looking at shoes, why don't we suppress all the other predictions? So we'll suppress all the accessories and bags, and we'll only look at the predictions for shoes. So you can see for the most part, the model is very good at picking up shoes. It has some false positives, and these are, bear in mind, these are high scoring, high confidence predictions. So they are correct. In some cases, actually picking up shoes that have not been annotated. So these shoes, this is a correct detection. but it was not annotated. So this is something to be mindful of. We might be detecting things that are not annotated in the data set. So this is an example of an image that is maybe requires re-annotating. So this is a way that you can use DataGrid to identify incorrectly labeled or missing labels in images. Okay, so let's take a look at some of the more advanced filtering with the query language. So if you wanted to debug false negatives in our model, so that's basically the image is present in, the object is present in an image, but our model fails to detect it. We could run a query like this in our data grid. So basically what we're saying is fetch all the images where the accessories column is not equal to 0. That means accessories are present in the image. And we can use an AND to combine a query over multiple columns. And return all the columns where score accessories is equal to 0. So that means that the model prediction assigned a score of 0 to the accessories class. So if we run this query, it filters out 187 images from our 500. So there's 187 images where accessories are present, but our model failed to detect them. So we can take a look at some of these accessories. We can perform the same groupings that we did before, but for now, let's just go through them to see if there's any sort of trend that might jump out. There are some where it looks like there's like a bit of occlusion in these accessories. It could be that they're like hats or very small parts of the image. So it seems like the accessories, at least in these two images, are small parts of the image. Like let's check over here. Well, here it's like very clearly not a small part of the image. So if we can, so it is actually. So it seems like accessories overall in this data set are actually small parts of the image. So that it might just be that this model that we're using just cannot pick up these small bounding boxes. What I want to show is how you can use the query to query metadata from images in the data grid. So as you recall, we had our detect script where we annotated our bounding boxes as well as our predictions to our data grid image. So if you click on a data grid image, you can see that these annotations show up in the UI and in this metadata dropdown. So this metadata is queryable through the query box. So if I run this query where I want to find all images with labels that contain the ground truth bags and images that contain the label ground truth shoes, I can do it in this way. So this means I'm selecting the image column, I'm selecting the labels with the labels metadata in the images, and I am running a contains check on the labels. So if I run this query, it will reduce my data frame down, my data grid down to 70 images. So these 70 images contain bags and shoes in the images. I can do things like group by, so I can group by accessories to see the distribution of scores for these images. So it seems like whether or not accessories are present, there's like basically a 50-50 split between this filtered group of images. And the distribution of MAP scores seems to be about the same, maybe slightly lower for images that do have accessories. And that's probably because the accessories are so small. We saw earlier that the accessory labels are so small. We can confirm this one more time. If I get rid of all of these labels, yeah, it looks like all these accessories are very, very small bounding boxes compared to the rest of the image. So we could, let's click on this image. Yeah, see, we completely missed accessories, predicting accessories in this image. So yeah, accessory prediction is hard. So we should probably try to find a way to improve our model performance on accessories. Um, so that with that concludes our walkthrough and demo of Kangas DataGrid. I hope you enjoyed it. There are several more tutorials in the works to try to show you how to use this amazing tool. We hope that you will find this useful in your computer vision workflows, and we welcome external contributions. It's worth noting that Kangas is completely open source. So if you see a feature or if you can think of a feature that doesn't exist yet and you want to see it, please feel free to open up an issue or pull request to suggest the feature, and we will very happily work with you to get that integrated into Kangas. And if you enjoyed this walkthrough, this demo, please like and subscribe to the Comet YouTube channel. We will be continuously posting a lot of video updates, so stay tuned.